Ever wondered how mathematicians categorize and group items? The answer is simple. They use sets. Sets are a cornerstone of mathematics, acting as a container of sorts where we can group anything from numbers to objects and even ideas. They're like the building blocks of the mathematical world, giving us a structured way to organize and classify. Imagine them as big invisible boxes where we store related things together. So, are you ready to dive deeper into the world of sets? Let's begin. But what exactly is a set? Let's find out. In the simplest terms, a set is a collection of distinct objects gathered together into one group. These objects can be anything: numbers, letters, animals, planets, or even other sets. The defining characteristic of a set is that its contents are clearly defined and distinct. For instance, consider a set of primary colors: red, blue, and yellow. This set is composed of 3 distinct elements, each a unique color. Here's another example. A set of the first 5 natural numbers: 1, 2, 3, 4, and 5. This set includes 5 distinct elements, each a unique number. Now, how do we depict a set? There are 2 common ways to depict a set: roster method and set builder form. In the roster method, we simply list out all the elements of the set, separated by commas, and enclose them in curly brackets. For instance, our set of primary colors would be written as red, blue, yellow. In the set builder form, we describe the properties or rules that define the elements of the set. For example, our set of the first 5 natural numbers can be written as x is a natural number and 1, x, a, and 5. Now that we know what a set is and how to depict it, let's move on to different types of sets. Did you know there are different types of sets? Yes, it's true. Just like the diverse species in the animal kingdom, sets in mathematics have their own distinct categories. Let's dive in and explore some of them. First up, we have disjoint sets. Imagine 2 circles that never touch or intersect. That's a visual representation of disjoint sets. In the world of numbers, disjoint sets are those that have no common elements. So, for example, the set of all even numbers and the set of all odd numbers would be disjoint sets. Next, we have infinite sets. As the name suggests, these sets have an infinite number of elements. Think about the set of all natural numbers. There's no end to it, right? That makes it an infinite set. Moving on, we encounter power sets. These are rather interesting. A power set of any set is the set of all possible subsets of the set. So, if we have a set with 2 elements, say apple and orange, the power set would include the empty set, the set of apple, the set of orange, and the set of apple and orange together. Speaking of the empty set, let's talk about it next. An empty set, also known as a null set, is a set that has no elements. It's like a basket with nothing in it. Last but not least, we have singleton sets. These are sets that contain exactly 1 element. If you have a set with just 1 apple, that's a singleton set. And those are just a few types of sets. Each one has its own unique properties and characteristics. It's like a mathematical zoo filled with diverse and fascinating creatures. But now you might be wondering, how do we compare or relate different sets? How do we know if one set is bigger, smaller, or equal to another? And what happens when sets intersect or unite? Well, hold on to your curiosity, because we're about to explore that next. Let's find out. Sets can be related to each other in many ways. Let's explore some of these relations. Think of sets as groups of items. They can overlap, be contained within one another, or be entirely separate. These relationships can be described through concepts like intersection, subsets, equal sets, and complement of sets. First up, intersection of sets. This is where 2 or more sets share common elements. Imagine 2 groups of students. One group loves pizza, and the other loves ice cream. The intersection of these 2 sets would be the students who love both pizza and ice cream. Next, let's talk about subsets. A subset is a set where all its elements are also part of another set. Take a set of all fruits and a set of all apples. Here, the set of all apples is a subset of the set of all fruits because every apple is a fruit. Moving on, we have equal sets. 2 sets are equal if they have exactly the same elements. It doesn't matter what order the elements are in, so a set of the first 3 prime numbers, 2, 3, and 5, is equal to a set that lists them as 5, 2, and 3. Lastly, the complement of a set. This is everything that is not in the set but is part of the universal set. Think of the universal set as everything under consideration. If we're talking about all animals and our set is all mammals, the complement would be all animals that are not mammals. These relations allow us to compare and analyze sets. They provide a structure to our understanding, giving us the means to group, separate, and relate different sets. But remember, while these relations help us understand the connections between sets, they are just one part of the story. Another tool we use to visualize these relations is the Venn diagram, but that's a topic for our next scene. Stay tuned. Venn diagrams are a powerful tool for visualizing relations between sets. Let's see how. In the world of sets, a Venn diagram is like a map. It's a simple yet incredibly effective tool that gives us a clear picture of how different sets intersect, overlap, or stand entirely apart. It's named after John Venn, an English mathematician, who introduced it in the late 19th century. But what exactly is a Venn diagram? Imagine circles or ovals drawn on a flat surface. Each of these shapes represents a set. Now, if these shapes overlap, it means the sets they represent have some elements in common. This overlapping area is called the intersection of the sets. If the circles don't overlap at all, it means the sets are disjointed, or in other words, they don't share any elements. For instance, let's take the sets of fruits and red things. The set of fruits would include apples, bananas, and oranges, among others. The set of red things, on the other hand, could include apples, roses, and cars. In a Venn diagram, these two sets would overlap at apples because apples are both fruits and red things. But Venn diagrams are not limited to just two sets. You could have 3, 4, or even more sets represented in these diagrams. The more sets you have, the more complex the diagram becomes, with multiple intersections and overlaps. Yet the principle remains the same. The areas where the circles overlap represent common elements between the sets. Venn diagrams are a great way to visualize the concepts of union, intersection, and difference between sets. They help us see at a glance how sets relate to each other, making these relationships easier to understand. After all, Venn diagrams are not just about understanding sets, they're about making sense of the world around us. They help us see connections where we might not have seen them before, and they make complex relationships simpler to grasp. Venn diagrams make it easy to understand the relations between sets, but that's not all there is to sets. Sets are an integral part of mathematics. Let's summarize what we've learned today. We started our journey into the world of sets by defining what a set is. A set, as we learned, is a well-defined collection of distinct objects, which could be anything from numbers to letters to fruits. We also discussed how to depict sets, be it through a roster or a rule method. Next, we delved into the different types of sets. We explored disjoint sets, which have no elements in common, and infinite sets, which, as the name suggests, have an infinite number of elements. We learned about power sets, which are the set of all subsets of a set, and of course, we cannot forget the smallest set of all, the empty set, which has no elements. Then we moved on to the relationships between sets. We learned how to find the intersection of sets, which is the set of elements common to both sets. We also discussed subsets, where all elements of one set are also elements of another. We learned about equal sets, where two sets have exactly the same elements, and the singleton set, which contains only one element. We also touched upon the concept of the complement of a set, which is everything that is not in the set. This is a particularly interesting concept as it expands our understanding of sets beyond just what is included. Our journey then took us to the realm of Venn diagrams, a useful tool for visually representing sets and their relationships. We learned how to use Venn diagrams to illustrate intersections, unions, and complements of sets, among other things. And that's a wrap on sets. Remember, sets are everywhere in mathematics. Next time you see a group of items, think about how you could represent them as a set. Until next time, keep exploring.